Yeah, thank you for the introduction. So actually, yes, we are we are from the Glaser group, and we're doing research in soft condensed matter and self-assembly thereof. And we primarily also do code development. And I'm presenting on our code HOOMD-blue, which is more of a soft matter code than MD is a biomolecular code. For coarse-grained systems, we do most of the work. And so it's open source code running on GPUs, as you may have guessed from this slide. And it's about scaling. So I'm showing you right up what I mean by scaling. And this is not on Blue Waters, but this is on the Cray XK7 at Oak Ridge. Later I will show how Blue Waters helped us to obtain results for the code development work. But this is scaling on the Titan machine. And we show you 3 types of simulation that can be done with HOOMD-blue as is. The first one is an MD type of simulation, scaling from 64 GPUs to about, okay, this is cut off on the screen. Yeah. So there should be a 16,384 on the right-hand side. So this is about 80% of the Titan machine. And this also works for a Monte Carlo code, a scalable Monte Carlo code, which Josh will be presenting in the second part on. That scales on the same range for hard particles, hard anisotropic particles. This is this example here. And finally, another variant or another code path in HOOMD is able to scale for hard anisotropic particles with a discrete element method of up to that size, and it uses an MD kind of integration here. So HOOMD is being used in a variety of different scientific contexts, and I'm just putting up this slide to give an impression how diverse the applications are. We have been seeing over 100 publications using HOOMD-blue as of to date, and it's primarily targeting soft matter research like knotting and active matter and not polymers. My own research as a postdoc in Minnesota focused on how to obtain the transition, the first order transition between the isotropic and lamellar state of diblock copolymer metals. And so this transition occurs here spontaneously between the isotropic state and the ordered state upon equilibration of the system. And what we were interested in is to see how this the temperature of this transition, or inversely, the chi parameter of the transition, is consistent between different coarse-grained models of diblock copolymer metals. And to that extent, we measured the free energy of the system as a function of some suitably defined order parameter, and also obtained the transition temperature, and this is another plot of the free energy. And the remarkable result was that all these 5 different coarse-grained systems at various different chain length and are giving rise to universal behavior over a remarkably wide range of invariant chain length. And this research necessitated about 500,000 service units, which we basically churned through within 2 months on the Exceed computer with using GPUs. And we wouldn't have been able to do this without using multi-GPU integration, using up to 300 some GPUs on this Kine machine. And so that set the stage for developing multi-GPU capable integration with HOOMD-blue. The approach we're using seems pretty standard at first. It's a spatial domain decomposition, which is also used in the LAMMPS code. And so it's basically dividing up the space into domains that are coupled via their boundaries, and they exchange particles periodically. And also, in order to correctly compute the forces, particles have to communicate their positions to neighboring domains when they reside in these ghost layers. And this requires communication. So I wouldn't be showing this slide because this is pretty standard if there wasn't a challenge behind it. And the challenge actually is more apparent when you consider comparison between CPU and GPU integration. So this is a situation with CPUs. This is a multi-core CPU, 4 to 12 cores, and they communicate by some network like InfiniBand. and this has a bandwidth of 6 gigabytes per second, and the other CPU sits here and they exchange information. So this is pretty much balanced, and this is why the reason why we see so many scalable codes on CPUs is that with so few cores, the compute throughput of a single processing unit is just not large enough to exhaust the bandwidth of the interconnect. With GPUs, the situation is drastically different. So GPUs have like thousands of cores on a chip, and so the question becomes: will this really be possible to scale a GPU code that runs efficiently on a single GPU to many GPUs? And as you may have guessed, the bandwidth of the network is staying essentially the same. So this becomes the limiting factor. And so from the start, it wasn't quite clear if we were able to actually achieve scaling on GPUs. And why this is so bad is also demonstrated in this plot, where we show the average time spent in different parts of the computation and communication as per time step as a function of the number of GPUs that participate in the simulation. And so first of all, we achieved like scaling neighbor and perforce kernels, which inversely scale with the number of GPUs, so then proportionally to the number of particles per GPU at constant particle number. However, the GPU the optimized kernels hit a barrier here because the communication is essentially constant as a function of the number of GPUs, and this demonstrates the kind of bottleneck we are seeing. And of course, we have developed various optimizations in HOOMD to overcome this problem, at least partially, as possible. And this shows the profile of the time step. So basically what we did is we used device-resident data structures. Very importantly, our kernels are completely auto-tuned on the fly. So the optimal parameter for execution is chosen during runtime by measuring the minimum execution time among a set of about hundreds parameters possible for every kernel. This takes about 30 seconds initially in the simulation. Then you end up with the optimal tuned kernel parameters. And also we do some overlap of communication and synchronous computation here. Yeah, so this works out as follows. So first of all, a weak scaling plot. Also, this is still on the Titan machine. Over a range of 1 to 3,000 GPUs. So this is again cut off here. We see a performance that is roughly constant within 50% for a system that has 32,000 Lennard-Jones particles per GPU. And that scales up to 108 million particles on 3,375 GPUs. Or 3,750, I think, yeah. And in strong scaling, the situation looks equally good after all these optimizations. So what I didn't mention that in the previous slide, I compared to LAMPS. This is again compared against LAMPS for 4 to 2048 GPUs. We see a strong scaling that is essentially linear in the regime up to 64 GPUs and continues up to 1,000 GPUs roughly. For a 10 million particle system, and this is consistently faster than LAMPS by a factor of 2x. So this quite impressively demonstrates the kind of effectiveness of our optimizations we put in there, which is more interesting even that on that machine and also on the Blue Waters machine, there's this MPS CUDA proxy flag, I think, or in short, there's a possibility to use many cores of a node to drive that single GPU that's inside a node. And LAMPS was initially optimized for this machine specifically to take into account the several CPU cores that drive the single GPU. And even with optimized settings, it's a 2x slower than this code, our code. Okay, and this is the same simulation. We ran both codes. With the efficiency is about such that we have 80% efficiency when there are at least 250,000 particles on a GPU. And of course, this is maybe a good value to justify in your compute type proposals. And also, yeah, so finally we go to a Blue Waters slide. This is a more complex example of a slightly more chemically realistic system of a polymer brush that is in the XY dimension here, and this is there are short chains tethered on the surface of this substrate, and so this simulation requires angles and bonds and dihedrals, and so the plot demonstrates actually that with even these more complex interactions, we get still essentially linear scaling, a 12.5x speed up over a CPU node, and a very good scaling up to 64 nodes in this case for about 500,000 particles. Finally, okay, we investigated GPU-direct LMA. I won't say much about this, except that GPU-direct LMA is promising, but it turned out to not mitigate the fundamental limitation of the PCIe bottleneck, which is still present. Although in double precision, which is slightly more bandwidth bound, this is again cut off here, it manages to be slightly about 10% faster than our manually optimized CPU host buffer copies. And again, a blue waters benchmark here, which demonstrates that with dissipative particle dynamics, first of all, we see some variation between different codes like HOOMD and 2 ports of lamps on GPUs in the range of about 64 GPUs here. But they basically converge into a similar behavior when we go to thousands of GPUs. And this connects to the first talk, where we also saw like some convergence, which was potentially more bandwidth and communication limited, which is occurring here as well. So basically, independent of which code is being used, we see similar performance. And this is even on 2 different kinds of machines. So both HOOMD was measured on blue waters, and LAMPS was the 2 LAMPS codes were Titan benchmarks. So this is more a statement about the machine and the reproducibility than it is about the codes. So we see about 10% fluctuations, variability between the jobs on the same machine. So this is about the error bars here. Okay, so to summarize my part, the multi-GPU support in HOOMD enables you to do large simulations and strong scaling on thousands of GPUs. And also GPU-direct LMA is maybe a step in the right direction, but not quite sufficient yet to reduce latency. And with this, Josh will tell us more about Monte Carlo on multiple GPUs.
Okay, thank you. So I'm Joshua Anderson. Yeah, that was Jens Glaser. So HOOMD does, Jens talked a lot about the molecular dynamics features in HOOMD, and just within our group, we've used those functionalities for a wide range of systems, from self-propelled colloids to tethered nanoparticles and the growth of icosahedral quasicrystals. And the one thing that all these have in common is your model is built up of point particles that interact via some potential. And in the soft matter physics field, oftentimes we make up our own potentials that are just phenomenological models to capture in the essential physics we need to describe what's going on. Another area that our group does a lot of work in is in particles that have shape. And so experimentalists can actually fabricate nano-size or micron-size particles that have facets or dimples, or you can pretty much draw a particle, and experimentalists can figure out some way to create it. And those types of simulations don't mesh well with molecular dynamics. We're working on those, but the easiest way to simulate hard particles with sharp facets is Monte Carlo. And so we have a long history in our group of using serial codes for Monte Carlo simulations. It's really easy to write a serial code that proposes a trial move to move a particle and accepts or rejects it. And that sort of limits how big of a simulation you can run, or how many you can, or how fast you can run it, even a small simulation if you want to run it very fast. So we're starting to get into million particle plus simulations now where necessary for long range correlations. And to do that, we first had to figure out how to parallelize Monte Carlo. Molecular dynamics is really easy to parallelize. People have been doing it for 50 years. Monte Carlo has existed just as long, but there's only a dozen papers that even attempt to parallelize it, and very few of them got it right. So we had to go back to the drawing board and sort of figure out how to take these systems and parallelize them effectively. And this, so I'm starting with the end first. So the end is we have a very general purpose hard particle Monte Carlo code that can simulate all of these systems and more, and integrates into HOOMD. Jens didn't mention in his part of the talk that HOOMD is actually built on Python scripting. So your job script to describe your simulation to the computer is just a simple Python script. And the difference between running a Monte Carlo and an MD simulation is you just change the type of integration routine you tell HOOMD to run. So it's the same code. The Monte Carlo code is using the same communications efficiency optimized communications algorithms that Jens talked about, but it's just built on a different integrator. So what is hard particle Monte Carlo? If you have no idea, the basic concept is in serial, you have a system configuration, you choose a particle at random, and you propose a random translation or rotation to that particle. And you can accept or reject it based on whether or not it overlaps its neighbors. In parallel, you want to propose multiple trial moves at the same time on in multiple cores on the GPU or on multiple domains in the CPU. And one easy way to do this on the GPU is to use a graph coloring. In 2 dimensions, you get 4 colors. In 3D, you get 8. And you can propose trial moves in the same color in parallel. And there's some tricks to figuring out how to actually still obey detailed balance in this scheme. And you can read my paper if you really want to know. The thing that makes Monte Carlo behave very different from molecular dynamics in a scaling perspective is that when your particles have geometry, looking at the interaction between 2 neighboring particles is a lot more expensive than just computing a pair potential between 2 particles. Leonard-Jones or DPD take a dozen flops. These methods to compute interactions between particles with faces or rounded particles take hundreds of iterations, and each iteration is hundreds of flops. So these are very compute intensive compared to molecular dynamics, which is very bandwidth intensive. And also, Monte Carlo, by its nature, is very random. And so when we implement this on the GPU, you end up with a very lot of divergence. And so this top panel is the first pass at implementing this. The yellow is time wasted where a trial move that was rejected no longer had to look at any other particles. And so we spent a long time coming up with a work queue partitioning scheme to take these reds are those expensive overlap checks I mentioned in the last slide, and to distribute them among threads in a warp so that you reduce that divergence. Okay, there's still divergence because these are iterative schemes. Some of them can finish in just 1 or 2 iterations, and some of them take 100 iterations. But there's very little that can be done about that divergence. I've tried. But at least this improves the performance greatly. So this kernel is relatively new. I just finished it in the last couple of weeks. So these benchmarks I'm going to show you are using the old kernel. The new GPU benchmarks are going to be significantly better, but I haven't had time to run those yet. So the scaling on Exceed Stampede, the even small systems, so I talked about at the beginning our long history running these simulations in the group. We typically run 2,000 to 4,000 particles in a simulation. Parallel simulations are really important even for that case, where you can take a 4,000 particle simulation and scale it up to 64 or even 128 processors on the CPU. That small of a system, it's really too small for a GPU. But now with GPUs, you can conceive of simulations of millions of particles that you could never even thought of before on the old serial codes. And then we developed this code a little bit on Blue Waters. We tested some large-scale weak scaling benchmarks. This is comparing the XE6 nodes to the XK7 nodes. And as I said, the new kernel probably makes us a factor of 2 much faster speed up. And the weak scaling kind of falls off at large node counts, and I'm not quite sure why that's happening. I haven't had time to examine that fully. But just to wrap up, right now the molecular dynamics features that were talked about in the first half of this talk are all open source. You can download it in HOOMD now. The Monte Carlo features are still under wraps, and they will be released open source soon. I don't know. I don't have a date or time. I'll open up for questions.
All right, let's thank both speakers real quick. Right?
When I was a young man, we used 162 particles, and we liked it.
Yeah.
Tell me how the science changes, going from 4,000, 400,000 to a million particles. What do you see that requires you, and where's the benefit in the science? Because that's the payoff rather than the...
Well, I'll answer that in terms of the Monte Carlo. So So for simulations like this, where you've got a fairly simple crystal forming, and we have periodic boundary conditions, 4,000 particles gives you a lot of unit cells. There's really no reason to run this system bigger at equilibrium. Areas where we're thinking about running the even simple crystals bigger is in looking at the nucleation and growth, trying to study those processes, those dynamic processes of a crystal growing to a large scale. So that's one new type of science we can do with bigger simulations. Another area where we need really big simulations is, this picture here is of the hexatic phase in 2 dimensions. So this is very, very slow decaying correlation functions, and you need to get the edge length of the box to be very large in order to resolve that correlation function, or just in order to determine what phase the system is in. So that's another important case where we need really large simulations. But you're right, there are a lot of cases where you can get by with very small simulations, and just going bigger doesn't give you any new science. So what we're looking towards is new types of science we can look at that we couldn't do before. Yeah, that's that'll be in next year's, because right now this was developing the code to make that science possible. So next year we'll have done that science, and we'll be talking about that.